10 year
So an
degree.
image like this, where we think we're looking at the cluster, we're really looking just at these galaxies that are kind of like sprinkles on this vast ice cream cone of dark matter. And we know the dark matter is there because it exerts this gravitational pull on the galaxies that we can see. All right, now we skip forward, and using Einstein's theory of relativity, I'll remind you that Einstein invented our notion of how gravity works through the concept that gravity is not just a force between two massive bodies. Instead, massive bodies or any kind of energy curves space-time in its vicinity, and other bodies move in that curved space-time, and that's how gravity gets communicated. And using that concept then led Einstein to predict, and then the first real verification of his theory, was that light rays should get bent in gravitational fields due to this curvature of space-time. And so what this means is if I look at a distant galaxy behind a foreground concentration of mass, say a cluster of galaxies, then the shape of that distant galaxy will get distorted because the light rays coming to us get bent by the gravitational field of that cluster. So something that's intrinsically elliptical, looking at the lower right-hand portion, that's behind the cluster and near the line of sight to it, will get distorted into something that appears more like a banana or an arc. And this has now been observed many times in observations from the Hubble Space Telescope and from ground-based observatories. So what you're seeing here is an image from the Hubble Space Telescope of a cluster of galaxies. Those are the big, bright galaxies. But then you also see these faint, wispy, very elongated structures, these arcs. And those are images of distant galaxies behind the cluster, and the light has been bent through the cluster, and that leads to these very elongated apparent shapes. And you can use those images to actually reconstruct what the mass distribution of that cluster of galaxies is. And so these sharp peaks are where the galaxies in the cluster are. But then in addition to those sharp peaks, you see this overall sort of mountain of matter. And that's all dark matter. That's the smoothly distributed dark matter in which these galaxies in that cluster are embedded. And so this is sort of direct confirmation of what Zwicky had found back in the 1930s. So skip forward now to the 1970s, and astronomers were studying the motions not only of galaxies within clusters, but of stars within individual galaxies. So this is the galaxy M33, spiral galaxy similar to our Milky Way. It's rotating around its center, and you can measure the rotation speed of those stars around the center of the galaxy. This was done by Vera Rubin and collaborators in the 1970s. And what's shown here is a plot of the rotation speed in kilometers per second as a function of distance from the center of that galaxy M33. Now what we expected is that as we move out from the center of the galaxy, the stars should be orbiting more and more slowly, because once you get far enough out, there's no more mass. It's just that you've enclosed all the stars. And so you would expect the rotation versus distance to look something like that lower dashed line. And that's very much what the rotation curve of our solar system looks like, of planets moving around the sun. The farther the planets are away from the sun, the slower their orbit, because gravity is weak. Instead, what Rubin and her collaborators found was that the rotation speed of stars around a galaxy keeps increasing and then sort of flattens out at a much higher value than would be expected just from the gravity of the stars contained within that galaxy. And this was again evidence that the bulk of the matter, of the mass in this galaxy, was not contained in the stars that we see, but was in fact contained in some broader distribution of dark matter. And so like Zwicky, Rubin found that the stars in a galaxy are moving faster than we can explain. The gravity of something that we can't see must be holding those stars in their orbits, and that's evidence for dark matter. In fact, galaxies are mostly dark matter. The stars that we see in these galaxies are like, again, sprinkles on this much larger mass of dark matter ice cream. And again, we know it's there because of its gravitational effect. again, skipping forward, just as we confirmed that fact in clusters of galaxies using gravitational lensing, we've also now confirmed the existence of dark matter in individual galaxies using the same gravitational lensing effect. So what you're seeing here are images of different galaxies, again from the Hubble Space Telescope. The yellowish blobs in the center is a foreground galaxy, and those bluish rings are actually the highly distorted images of another galaxy behind that foreground galaxy. And it's been distorted because the light from that distant galaxy was bent around by the mass of the foreground galaxy. And that very high lensing is again telling us about how much mass there is within the foreground galaxy, much more than the mass contained. Here's another example of this. This is actually a system we found with the Sloan Digital Sky Survey, and then followed up using the Hubble Space Telescope. So again, the yellowish blob in the center is the foreground galaxy. The blue ring around it is the highly distorted image of another galaxy that's behind it. Okay, and finally we now do this on a kind of industrial scale, where we can apply that same technique of lensing to study the shapes of galaxies behind thousands of foreground galaxies. We do this in a kind of average statistical sense. This is called galaxy-galaxy lensing. And instead of probing the masses of individual galaxies, this lets us probe the sort of typical mass of average galaxies. And so we started using this technique back in the 1990s. And what we found, again, was that on average, luminous galaxies are embedded in these extended, what we call halos of dark matter. And so this was written up in the New York Times in late 1999. And apparently we were very surprised by this finding, because that, to make it interesting for there has to be some element of drama. I was actually much more interested in the article on prehistoric fashion. That was the other article in the newspaper that day. Okay, so we've now established that dark matter exists as the dominant form of mass in galaxies and in clusters of galaxies. So the natural question is, what is dark matter made of? Is it made, so what could it be made of? Well, the stuff we know about in the universe is atoms, which is made of electrons orbiting around a nucleus. The nucleus, more fundamentally, is made of protons and neutrons. The protons and neutrons, more fundamentally, are made of quarks. And so you might think, okay, maybe dark matter is made of some kind of atom that just, for whatever reason, is not shining light or emitting or interacting with light in some way.
これなんか未例のあれみたい。
Something that's very dark.
今
And so in early times, people thought, okay, maybe there could be very faint stars that we just too faint to see. Maybe planets that aren't illuminated by a nearby star. Maybe some kind of dirty rocks. And so it's time for a search for these. But we gradually concluded that there simply aren't enough atoms in the universe to account for all of the dark matter that we infer in galaxies and clusters of galaxies. There's too much dark matter out there compared to the amount of atoms that we have added up in the universe that we've now measured very precisely. The dark matter must be made of something other than atoms, or more fundamentally quarks, the things we study here in Fermi. And perhaps it's made of some new kind of elementary particle that we've never seen before, that isn't, the atoms aren't composed of. And so our name for this is weakly interacting massive particle, or WIMP. And so WIMP is basically some new kind of elementary particle. It might be, say, 10 to 100 times the mass of a proton, which is so weakly interacting that we don't see it. It doesn't shine. It doesn't interact with light. But it could interact via the weak interaction with ordinary kinds of ordinary elements. And so there are experiments around the world, sited deep underground, filled with atoms, as you've seen here. And they're looking for these WIMP particles coming from the dark halo of our galaxy. And the notion is that occasionally one of these WIMPs would come in, knock into the nucleus in an atom in this detector, and impart some energy into that nucleus, a very tiny amount. But if you have a sensitive enough detector, you can detect that energy that's deposited. And so there are a number of experiments now going around the world. Fermilab has an active program in searching for these dark matter WIMPs using these techniques. There are a variety of different techniques. They all involve people wearing funny hats. This is an interesting field. There have been some of these experiments have claimed to have seen dark matter particles. Others that we think are more sensitive have not yet. So it's an interesting time, and these experiments are getting more and more sensitive. And there's a hope that in the next decade, perhaps, we may actually detect in a verifiable way these dark matter particles. Another possibility is that we may actually produce these dark matter particles. You've all heard of the Large Hadron Collider at CERN, our sister laboratory in Switzerland, where the Higgs boson was discovered in 2012. They're bashing protons together at very unprecedentedly high energies. And the hope is that perhaps in one of these collisions of protons, they may produce dark matter particles, WIMPs, that we could infer through their signatures in these colliders. A third possibility for detecting dark matter is that we may see WIMPs annihilating with each other. So our current theory suggests that if there are dark matter WIMP particles, there would also be antiparticles floating around in the halo of our galaxy. And whenever a WIMP particle and antiparticle come close together and collide, they would annihilate, giving off a burst of energy, which would lead to radiation, high energy radiation, say gamma rays, that we could see if we have a gamma ray observatory. So NASA has such a gamma ray observatory orbiting the Earth, the Fermi Gamma Ray Satellite. And Fermi has been looking for signs of these anti-WIMP annihilations, looking both at the center of our Milky Way galaxy, which is very dense, so there may be a lot of dark matter there, and also looking at these other dwarf neighboring galaxies to the Milky Way, which are also very dense and would be places to look for this kind of annihilation signal. So Fermi is in the process of looking for gamma rays coming from WIMP annihilation. Okay, continuing on with the context, setting the basic facts of our universe. The fourth fact is that the universe is expanding. And this is traced to the work of Edwin Hubble. Hubble was an astronomer in the first half of the last century. And we have to talk about him because he was a graduate of the University of Chicago. Both his undergraduate and graduate degrees were there. He also studied law. He was a boxer. He did track and field. He played basketball in his spare time. He did astronomy. And Hubble did some really amazing feats in observational astronomy in the first part of the 20th century. He's the one who really proved that spiral nebulae, these wispy things, which we now call galaxies, he's the one who proved that they are actually galaxies outside of our own Milky Way. Before then, there had been great uncertainty whether these nebulae were actually clouds of stars within our own galaxy. And he discovered the expanding universe in the late 1920s and went on to make important catalogs of galaxies in sky survey. So here's a picture of Hubble using the Palomar 48-inch telescope. So has anybody noticed anything odd about this photograph of Hubble using the telescope? Well, he's not looking through the telescope, he's looking through the viewfinder, but yes, exactly. The lights are on. So to do astronomy, the lights have to be off. They have to be dark. So, I sort of have my doubts about, how authentic all this stuff really is because, you should have known to turn the lights on. Anyway, before that, Hubble had a quite stellar athletic career. So here's Hubble with the 1909 National Championship, before the NCAA, I think, National Championship basketball team, 1909. And here is actually Hubble's championship basketball on the space shuttle with the Hubble Space Telescope in the background. The final score of that championship game was University of Chicago 18, Indiana 12. I think it took them a while before they, Steph Curry hadn't been invented yet. They didn't have three-pointers back then, so nevertheless, Hubble really went on to a brilliant career in astronomy, and to celebrate his career, astronomer John Grunsfeld, also a Chicago graduate, brought his basketball up to on one of the missions where they refurbished the Hubble Space Telescope. Okay, so here's the expanding universe. As time goes on, everything in the universe is moving away from everything else. If you were to run this movie backward in time, eventually everything would be on top of everything else. 13.8 billion years ago, that's what we call the Big Bang. And I want to stress a few key points about the expanding universe. One is we're really talking about the distance between galaxies increasing. We don't think our galaxy is expanding. We don't think this room is expanding. I'm expanding, but that's because I eat too much. Generally, within our galaxy, gravity is keeping things sort of stable. So it's really the distance between galaxies that's increasing with time. And again, to give you a sense of scale, a galaxy 100 million light years away is moving away from us at 2,000 miles per second. So the universe is kind of humming along. Again, this was really established by Hubble in the late 1920s. Now, there are a lot of misconceptions about the expanding universe, and often many of these misconceptions are traced to the fact that this picture, while useful, we have to be cautious in interpreting it, because we're looking at a lower dimensional universe from our three-dimensional perspective. We don't think the universe has a center or an edge, at least not that we can see. It looks the same everywhere. It's homogeneous and isotropic. And the expansion is happening everywhere. It's not exploding into empty space. And so really that picture of an expanding balloon is somewhat misleading. It's probably better to think of, say, an infinite raisin bread. Think of the raisins as galaxies. You put enough yeast into it and put it into the oven, and it will start to expand. Each raisin will move away from all of the other raisins. That's probably a better analogy for the expanding universe. Another point to make is that as the universe expands, like any gas, it gets less dense and it cools off. Backward in time towards the Big Bang, it becomes hotter and denser. So today the universe is very cold. It's only 3 degrees above absolute zero and very diffuse. The density of the universe is very low. But in the early universe, it was much hotter and much denser. And so this is now our best picture of the early universe, cosmic microwave background radiation. This is a scene from the Planck satellite. So this is an all-sky image of the temperature of the universe as it appears today, 3 degrees above absolute zero. So the red and blue splotches are regions where the temperature is slightly hotter and slightly colder than the average. And that slight is only 1 part in 100,000. So the universe's first approximation has the same temperature everywhere, but it has slight differences in temperature from one place to the other. Now this is really giving us a snapshot of what the universe looked like when it was only 380,000 years old. It's now 13.8 billion. So this is really a picture of the adolescent universe. And at that time, it had a temperature of a few thousand degrees. But since then, with the expansion of the universe, it has cooled to a temperature of 3 degrees above zero. So this is a picture of what the universe looks like today. This is a map of galaxies from an infrared survey done a number of years ago. Each of the little white squares there is the location of a galaxy. There's a few million galaxies in this picture. The blue is just, this is in funny coordinates, so the blue is actually infrared emission from our own galaxy. And again, what you see here is that the universe today is actually quite lumpy. It's not obvious what the contrast is here, but the lumpiness of the universe today is orders of magnitude larger than it was 380,000 years after the Big Bang. And so our picture is that as the universe has evolved, it started in really homogeneous conditions. The density of the universe is almost the same everywhere in space. but then over time, gravity acted on slight differences in the density between different locations in space. Regions that were denser than average accrued matter onto them. Regions that were less dense than average became more and more vacuous. And eventually, large-scale structures formed. This kind of web, this thing we call the cosmic web. So this is a computer simulation of the evolution of structure from nearly homogeneous initial conditions to a very inhomogeneous universe that we see today. And in this simulation, the only ingredients are gravity acting on particles and dark matter particles, for example, wind. They didn't even bother to put in atoms in this simulation because they're a small minority compared to the dark matter. And this simulated universe looks remarkably like that lumpy universe of galaxies that we actually see today. So our picture of the history of the universe is that it started in a Big Bang 13.8 billion years ago, started expanding very rapidly. That's a period we call cosmic inflation. Once it had reached about 380,000 years after the Big Bang, that's when the photons, the radiation in the microwave background started streaming away from the atom, and that gives us this picture of the microwave background that we saw from Planck. And then over the succeeding billions of years, those small fluctuations in the temperature and density of the universe evolved via gravity into the large-scale structures we see today: galaxies, stars, planets, and larger-scale structures. So that's the picture we have now of how the universe has evolved. So we know the universe is expanding, and it's natural to ask, is the expansion changing over time? So what do we expect? Well, again, gravity is the dominant force on large scale. And so we can do a simple thought experiment.